All right, so let's look at some of the ramifications of keeping the speed of light constant. And in this example, let's say that we've got a rapidly moving object, say it's a rocket ship, moving at 80% of the speed of light. Okay, now, turns out, and this is something that we're going to be able to show soon, is that no material object can go faster than the speed of light. But for the moment, we're not going to assume that. We're just going to keep the speed lower than light so that no contradictions occur. And so as this rocket passes by this observer on the Earth, we're going to look at an event which takes place. So that event is a light beam going across and back across the rocket ship. So here, the rocket traveler shines the light beam. The light beam travels through this distance. Okay? And so this distance then is equal to the speed of light times the amount of time that it elapses on the rocket's clock. Okay? And so that's the time that it takes for the light beam to move across the width of the rocket ship, moving at the speed of light. Okay? And so that's what the rocket observer sees. What does the Earth observer see? Well, the Earth observer sees that the rocket, while that light beam has moved across the rocket itself has moved a certain distance. Rate times time equals distance. So we'll call that distance Vt, where t is the time that's measured on the Earth's clock. Okay. And here, this is the time that's measured on the rocket's clock. Okay. And so that means then that if the rocket's moved this far, the light beam relative to the Earth has moved along this hypotenuse path as measured by the person on the Earth. So if we draw this triangle, it's going to have a base side Vt, it's going to have a vertical side, which is the width of the rocket ship, that's equal to Ct, and then the distance across the hypotenuse, what is that? Well, normally, if we weren't going to require that the speed of light stay constant, we'd say, well, the speed of light is just moving faster in this frame of reference than the normal speed of light. We would say that the light beam has a component of velocity c in this direction and a component of velocity v in that direction, so therefore the hypotenuse is faster than the speed of light. But no, Einstein says you can't do that because that violates the laws of physics, basically. It says that the strength of the magnetic and electric forces will be different if you're traveling at different speeds. So we can't have that. And so instead, we're going to have to courageously write this as the speed of light times the time. However, if we do that, because the rate times time equals distance, but if the speed can't change, and this distance is bigger, then that tells us that the time that's being measured in the rocket's clock must be different than the time that's measured on the Earth's clock. So if we call t here the time that's measured on the Earth's clock, and we see here that t naught is the time measured on the rocket's clock, then they can't be equal. And so therefore, we can say that t must be greater than t naught, so that more time elapses on the Earth's clock than elapses on the rocket's clock. That's the only way to maintain the Pythagorean theorem. And we make this implicit assumption that the laws of physics follow mathematical rules and that it doesn't break the rules of mathematics. Okay, and so you can't have a right triangle that has a hypotenuse that's longer than one of its base sides. That just, you know, Pythagoras wouldn't like that. And that you just can't do that and maintain this basic rule of mathematics. And so therefore, more time than elapses on the Earth's clock than on the rocket's clock. So time is relative. Okay, and this is as viewed by the Earth. So what do I mean by that? We've got to be very careful here what we mean by T and T naught and who's viewing what. Because the rocket's going to see something completely different. But if you're from the Earth's point of view watching this happen and this beam go across the rocket ship, then you can see on your closed circuit TV monitoring camera a clock ticking off. So T naught is the time elapsed on the rocket's clock viewed from the Earth. And similarly, this time that elapses on the Earth's clock is also viewed by the Earth. So the Earth then is making a comparison. The Earth is saying that there's more time elapsing on their own clock than there is elapsing on the rocket's clock. And so therefore, because more time is elapsed, and there's less time having elapsed on the rocket's clock, then that means that time is moving more slowly on the moving object. So if you're going to keep the speed of light the same, then time has to be relative. You can't just have one clock that ticks off the same everywhere in the universe. And so that means that everybody's reality is going to be different because everybody in the universe is going to be moving with different speeds, and so they're all going to see different times. That's why they call it relativity, because everything's relative to your point of view. You know, how much time elapses depends on how you look at things. So the conclusion then is time slows down for a moving object. And so how would this manifest itself? Well, it would manifest itself by less time clicking off on the rocket's clock as viewed by the Earth, but it will also manifest itself by the astronaut moving in slow motion relative to the Earth. So if you took a video of that astronaut, you'd see him or her moving at a slower rate. And so that's a little bit counterintuitive in a sense, because the rocket is moving so fast. But then if you could look inside the rocket and see what the people are doing, see the clock's moving more slowly and the people are moving in slow motion. So the question then is, by how much is the time slowing down for the moving object? So if we go back to this equation, or to this picture, we can set up an equation using the Pythagorean theorem. We can say that c squared t squared equals v squared t squared plus c squared t naught squared. And so here, basically, we're just satisfying the Pythagorean theorem where this time must be the time is measured by the Earth's clock because this distance is 0 from the rocket's point of view. The only thing that the light beam is doing is moving across the rocket from the rocket's point of view. And so this allows us then to solve for t in terms of t naught. And when we do that, we get t squared times c squared minus v squared is equal to c squared t naught squared, or t squared is equal to c squared divided by c squared minus v squared times t naught squared. So we do a little bit of algebra here. Divide numerator and denominator by c squared. That gives us 1 divided by 1 minus v squared over c squared. We get t then is equal to the square root of that times t naught. Okay. And so that then shows us that, or another way of writing this is t naught divided by the square root 1 minus v squared over c squared. So this tells us then that t is greater than t naught because 1 minus v squared over c squared has to always be less than 1. And you're dividing by something that's less than 1. Unless, of course, v is 0. If v is 0, then t and t naught are going to be the same. And so this brings up some kind of astonishing conclusions. One of the conclusions that we can draw from this is that time intervals are not absolute, but depend on the relative speeds of the objects observed. Okay, so you don't have an absolute clock. The speed of light is the maximum speed that anything can go. Now let's just go back to this equation and see why that's true. Let's say that v were greater than c. If you could go faster than the speed of light, let's see what that does to this equation. Then let's just look at the square root factor, because that's where all the trouble is created. So let's say, for example here, that v is equal to 2c, okay, double the speed of light. Then our square root factor would look like 1 minus 2c squared over c squared. That would be square root of 1 minus 4. That would be the square root of negative 3. And so that's not a number. That's square root of a negative number is not a real number. And so although you have learned that we can say that's the same thing as what? Square root of 3i, that cannot be used to define anything physical in our reality, because you need to have an actual real number to define a real physical quantity. And so, because this is imaginary, means that you're breaking another law of mathematics. So over here, we can't break the Pythagorean theorem. Over here, we can't have the square root of negative number describe something that's physically real. Okay, and so that shows us that v can't be greater than c. Now, I'll give you a more physical argument for this later, but this is just a mathematical argument. Will be good enough for now. And so the other thing we could say, well, what about v equaling c? If v were equal to the speed of light, then you get the square root of 1 minus c squared over c squared, which is the square root of 0. So it seems like that's not creating any problems until you put it back into this equation and you see that t then goes to infinity. Okay? Because you're dividing by 0 and the limit as v goes to c. So that means that you can't go the speed of light or greater than the speed of light. So v then must be less than, but not equal to c. Can't be equal either, otherwise you're dividing by 0. Okay? And so that's why we say that the speed limit is 3 times 10 to the 8 meters per second in the universe, because we can't have our times going imaginary, and we don't want infinite time to pass either. Okay, and because then we'd be dividing by 0. So let's go back and see what some of the other implications of time dilation are. Well, people in different reference frames can agree on important observational data. Okay? But every observer is still correct from his or her own point of view. So that means that although you may have a completely different account of something than somebody who's moving at a different speed, you're both right. And so that means that there are a lot of relative realities. There isn't just one absolute reality. Okay, so c is fastest speed, and we have relative realities. No one absolute reality. And so this is something that philosophers probably wouldn't like very much. You know, but we didn't know about this until 1905, and so the philosophers are just going on and on for ages and ages, trying to come up with one absolute reality for everything, and Einstein proved that that's non-existent. There is no such thing as a single absolute reality. So, getting away from the philosophical aspects of this for a moment, let's do an actual calculation. Let's say that t naught equals 60 seconds in the last example, where we've got that rocket moving at v equals 0.8 c. So we're okay here in that we're not going faster than the speed of light. And so let's say then that the clock goes all the way around once, 60 seconds. So you're watching that from the Earth's point of view with your clock. This is t naught. And then you're watching with your clock and you're checking it out. You're expecting it's going to go all the way around once and then some, right? And so let's find t. If t naught is 60. So that shows us how much more time elapses on the Earth's clock than the Earth sees elapsing on the rocket's clock. By the way, I want to invite you to come by my Zoom office hours and we can talk about some of this stuff, because if this makes sense to you, then maybe you can explain it to me. Okay, so let's do this now. We'll say t is equal to t naught divided by the square root of 1 minus v squared over c squared. Okay, and now we're going to plug in for v, 0.8c, and t naught is 60 seconds. So let's do the square root part first. Square root of 1 minus 0.8c squared over c squared. That would be square root of 1 minus. Now here you could put in the 3 times 10 to the 8 meters per second for c, but a lot of times in these expressions, if you just leave it in terms of c, then the c squareds are going to cancel. It makes your numbers so much easier to work through. So this then is just going to be 1 minus 0.64 c squared over c squared. So the c squareds are going to cancel. So that'll give us square root of 0.36, which is just 0.6. So our square root factor is 0.6. And so if we plug this in now, with t naught being 60 seconds, divided by 0.6, what we get, because this is 10/6, right, or 6/10 I should say. So 60 divided by 6 is just 10, and then the 10 in the bottom flips up, so it's 10 times 10 is 100 seconds. Okay, so that's how much time has elapsed then on the rocket's clock. More than 1.5 times as much. We're up here. This is 90 seconds. We're going around once. 60, 90, 100 seconds. Whereas here only 60 seconds have gone off on the rocket's clock. Okay. And so that's a simple calculation then that we can do to show what's happening with time dilation. Okay. So you might wonder then, well, is that the only thing that gets messed up by keeping the speed of light constant? Or is it only time intervals that are changed? And the answer is no. Also, lengths are going to change too, because the velocity that you're calculating for the speed of light, that's distance over time. And so that means that distances are going to have to change too, because you're trying to keep the speed of light constant, and it's distance over time. All right, so given the time state are adjusted, let's take a look at another kind of problem. And in this one, let's say that we have a mu meson that is created in the Earth's upper atmosphere. And a mu meson is a heavier version of an electron. And so it's basically, it's just like an electron, but it's in what we call another family that has higher mass. And these mu mesons can be produced if you get enough high-intensity solar radiation striking a lighter particle. Okay? And so these can be created from the high-energy flux of radiation coming from the sun. But before the atmosphere has had a chance to interact with that radiation in the upper atmosphere. So let's say that's where the mu meson is produced. And the mu meson has a lifespan. It's unstable. Something like 2.2 microseconds. Okay, so this means 2.2 times 10 to the minus 6 seconds. That's, on the average, how long a mu meson lives. Being a heavier version of the electron, it'll tend to decay down into lower energy states that'll give off other particles like electrons and neutrinos and things. And but this is how long it lasts as a mu meson. And so here's the puzzle with this, is that it only lasts 2.2 microseconds, and the thickness of the Earth's atmosphere, say, is, well, let's say 200 miles, maybe 300 kilometers. Be the thickness of the Earth's atmosphere that would have to move through. If you figure out how much time it takes, even if we're moving at the speed of light, and we know they can't be going that fast, right? Even if we're going at the speed of light times the time would equal 300 times 10 to the 3 meters, or the time would be equal to 300 times 10 to the 3 divided by 3 times 10 to the 8. Okay, so that's 10 to the 5, 10 to the 8. So that's 0.001 seconds. Okay, so that's 1,000th of a second, or almost 1,000 times the lifespan of the mu meson. Okay, and so we would conclude from that that mu mesons that are produced in the Earth's upper atmosphere could never make it to the surface because they just don't live long enough to make it to the surface. However, this is the paradox, or the, you shouldn't call it exactly a paradox, but here's our puzzle. Let's call it a puzzle. We find that many mu mesons make it to the Earth's surface. Okay, and so you say, well, that's really not a problem, because the clock on the Mume-san that's determining its lifespan, it's like a regular clock that you have in a rocket. So if you're watching that from the Earth, you're going to see that clock ticking off more slowly. You say, well, it only lasts 2.2 microseconds on your clock, okay? But it's going to be a lot more than that on the Mume-san's clock. It's a no problem. So this distance then is going to equal rate, and let's just say it's going the speed of light, even though it's not going that fast, just as a maximum speed times the time. Okay? And so that time is going to be the 2.2 microseconds divided by the square root of 1 minus v squared over c squared. So basically what we see then, or if we call this v in general, we say that this is v times t equals x. Okay. And so then you can adjust the velocity in such a way as to make the 2.2 microseconds divided by that very small number equal to a millisecond, right? Because the clock here is moving more slowly than it is from its own point of view. And so therefore, the 2.2 microseconds is expanded from the Earth's point of view. So this is what the Earth sees. It sees the Mume-san live longer than 2.2 microseconds. By a factor of that square root thing. So v then has got to be pretty close to c, because that number is going to have to be like 1/1000th or something. You know, it's going to have to be a really small number, and then you'll divide by that really small number. That'll give you a really big number for the time. So this is v then times t equals x. Okay, so that's from the Earth's point of view, much bigger time because the object is moving. However, if we're going to stay consistent with Einstein's postulates, then we must also be able to flip into the reference frame of the Mume-san and get the same observation, that the Mume-san makes it to the surface. Okay, so in the Mume-san's frame, the Mume-san's not moving. And it's the Earth that's moving up toward the Mume-san at a velocity v. So this is the Earth's surface moving toward the Mume-san. This was in the Earth's frame here. This is the Mume-san's frame. So in the Mume-san's frame, the Mume-san's time is only 2.2 microseconds. So it's got a little tiny time. It's got the same velocity, because the velocity, which is almost the speed of light, is the same relative velocity whether it's the Mume-san moving toward the Earth or the Earth moving toward the Mume-san. And so the only way to make this consistent with the fact that it does make it to the surface is to have a contracted length, which I can call here x. Okay. But that x can't be the same as this one, right? Because this one is the original x here. So I'll call that x naught. And this is the contracted x, which is a smaller number. which I'll call x here. Okay, so this is the regular x, which I'll call x naught because that's how big of a distance you go when you're in the same frame of reference as this bigger distance. But now you're in the mu meson's frame of reference, and now the x value is contracted. And so, but the velocities are the same. So we can say that this is t naught now. Okay, so this is the regular time. This is the 2.2 microseconds, which is the proper time when there's no velocity, because relative to itself, the mu meson isn't moving. It's the Earth that's moving toward the mu meson. So the mu meson's time is just the regular time that you would get if you're in the same frame of reference as the clock. The mu meson's in the same frame of reference as its own clock. So therefore, v is equal to x over t naught. But from this equation, it's also equal to x naught over t. Right? And so x naught is big and t is big. So the velocity in the case of you watching the mu meson from the Earth's point of view, in other words, is a big distance over a big time. But from the mu meson's point of view, that same velocity is a little distance over a little time. But they have to be equal to each other because the relative velocity of the Earth moving toward the mu meson is the same as the relative velocity of the mu meson moving toward the Earth. And now, in the textbook, they go through a much more complicated way of determining the length contraction. But I think this is the most straightforward. And so here, I'm just going to solve this for x. This gives me the contracted length from this equation. So that's going to be equal to x naught times t naught over t. But t is just t naught divided by the square root of 1 minus v squared over c squared. And so that's just, the t naughts cancel, and this is in the denominator, so it flips up. That's just x naught times the square root of 1 minus v squared over c squared. So we see then that time intervals expand because t is equal to t naught divided by the square root 1 minus v squared over c squared. So time intervals get bigger, they expand, but lengths contract. Okay, so what does this mean physically? Well, let's say that I'm moving along with a meter stick. And I'm running along, let's say, at 0.6 c. So here I am, running along at 0.6 c, holding the meter stick, like that. And so as I run across the room, say I had a lot of coffee to drink, and I'm able to get going at super fast speeds. So I start running like this. What's going to happen, I wish I had a telescoping meter stick, is that the meter stick's going to get shorter. I'm going to get skinnier in the direction of my motion, which is okay with me. And so here we've got this as L naught. Okay, so that's the original length. But now if we start this thing moving, it's going to get shorter. So this is L. This is our contracted length. And now look, the runner is skinnier. He's got an oval-shaped head. He's running along, let's say, at 0.6 c is the velocity. Like that. And so L then is going to be less than L naught. Or I call this x naught, just to stay consistent. what I was calling the distances before. And then this is x. And then we've got x is equal to x naught times the square root of 1 minus v squared over c squared. So let's ask then, from the Earth's point of view, how fast is the, how short is the meter stick? So this is from the Earth's view. All right, so I did this with a slightly different number. .6c instead of 0.8c. So what's x naught? Well, if it's a meter stick, that's just 1 meter. So I've had people ask me this question before on exams. I say, there's a meter stick moving at such and such a speed. They go, what's the length of the meter stick? Well, we know, it's 1 meter, right? So you need to ask me about that one. Right? Use a meter stick example. All right, so this is 1 meter then, times the square root of 1 minus 0.6c squared over c squared. Okay, and so that would be 1 times the square root of 1 minus 0.36 c squared over c squareds cancel again. And so that would be square root of 0.64, which is 0.8. Okay, so my square root factor in this case is 0.8, and so therefore x is equal to 1 meter times, it's been contracted by 20%, so that's 0.8 is my correction factor, and so therefore the answer is 0.8 meters. The meter stick is 20% shorter than it was when it wasn't moving.